Hi, my name is Roberto Rodriguez Rivas and I am an STA candidate. I'm going to present this class on chi-square test, the whens, the whys, and the hows. So, chi-square, first of all, we need to talk about statistical tests and their overall objective. Their overall objective is to test an hypothesis, okay? This hypothesis, the base hypothesis of all statistical tests, is the null hypothesis. There is that there are no difference between two or more groups. We can compare, contrast different types of variables, but at the end of the day, what we want to see is if there is or there is not difference between two or more groups. This is part of the inferential statistics, okay? So the first thing we have to do is to choose the right test, okay? The two initial steps of choosing the right test, first one is knowing your variables, sorry. So how will you know your variables? You need to look at your research question, okay? From your research question, you're going to take out the dependent and the independent variable. The independent variables are the variables that the most important variable of your study that is going to influence the outcome, okay? The outcome per se is the dependent variable at the end of the day, okay? So as a little exercise of, of choosing the dependent and independent variable, we're going to do it a little later, okay? While classifying our variables, we have two main groups that we can talk about that are qualitative and quantitative variables. Okay, qualitative variables can classify into nominal or ordinal, and quantitative, discrete, and continuous. Each one of these variables has different objectives at the end of the day. The nominal variables are used to classify, while ordinal variables are used to hierarchize. Okay, discrete variables are used to count because they are rounded up numbers, and continuous variables are mostly used for measure. As you know, nominal variables are the ones that classify things, for example, gender, all right? Female or male. There is no hierarchy over gender, of course, and it's only used to classify things. In this case, people. Ordinal variables can be an example of them can be, for instance, educational level, because there is an order in educational level, like primary, elementary school, and middle and high school, okay? Discrete or counting can be used for a number of cars that go over an hour in this road, okay? 1, 2, 3, 4, 5, and continuous that are used for measure can be, for instance, weight in kilograms or meters or miles. And examples of this research question can be as follow. Is intervention X effective in reducing the mean concentration of interleukin-6 in patients with COVID-19? Okay, so from this we can take two main variables: the intervention, that is intervention X. Whether or not the patient has this intervention is then a qualitative variable, okay? It's a nominal variable, yes or no. And the intervention, and reducing the mean concentration of interleukin-6, the word mean is giving you, all right, it's giving you the clue that this is going to be a continuous variable. Next example is teleeducational program. A teleeducational program is the intervention, as is our independent variable, okay? In this case, we have our independent variable here and our dependent variable here. Is teleeducation program effective in reducing the number of failed students in the headache program of a hospital X? So the number of failed students is the dependent variable, okay? The independent variable is the educational program. Is the intervention is the independent, both with I. Okay? And then is periodizational edema a risk factor for epileptic status in patients with NCC? In this case, periodizational edema is going to be our independent variable and epileptic status our dependent variable. Okay? Periodizational edema is yes or no situation, all right? Then it's qualitative and nominal. And epileptic status is also a yes or no situation, which means that it's also qualitative and also nominal, okay? So for the test, you now know which variable you're going to use. For instance, let's take the last question we used. Is periodizational edema a risk factor to cause epileptic status? So we have two variables, okay? Two variables that are qualitative and nominal. So we want to compare two different groups, the ones that are receiving and or not the intervention, and we are looking at binomial outcomes, okay? This means that this data is qualitative and nominal, binomial in this case. We have to choose what is our goal at the end of the day. We are not describing one group, we are not comparing one group to a hypothetical value, we are comparing two unpaired groups. So in this case, we have a couple of tests that we can use, in this case Fisher or chi-square test. We are talking about unpaired data. That's one of the things you have to decide. Unpaired data means that, okay, it means that the two groups are not dependent one of each other. For example, paired data can be multiple measures in the same patients, pre and post intervention measurements, for instance. In this case, it's unpaired data, two groups to be compared, not more than two groups. We can choose between chi-square test or Fisher exact test. Okay, the chi-square test is a test in dependency between two categorical variables, which we have seen now. The categorical variables are often described in frequencies, percentages, or fractions, okay? It's a non-parametrical test and compares observed frequencies with expected frequencies. What do we mean with this last sentence? What is observed frequencies with expected frequencies? Often to use a chi-square test, when we have two categorical variables that are expressed in frequencies, we can use a contingency table like the one in the picture, where your independent variable goes in the left side of the table and your dependent variable at the top of the table, okay? Since both are binomial, these are yes or no situation, you have four different cells, A, B, C, or D, and the totals of each columns and rows at the extreme parts of the table, okay? In this case, our chi-square test works with this hypothesis. The null hypothesis, that is the base hypothesis of the test, that studied variables are independent of one another, and the alternate hypothesis is that the studied variables are not independent of one another. So all statistical tests, as I said before, assume that the null hypothesis is correct, and you're going to reject the null hypothesis when the p-value is less than 0.05 or other selected cutoff point. The advantages for chi-square is that it is a simple test, it can be calculated manually, it allows for comparison using 3 or more categories. That is very important because Fisher test only allows you to do 2 categories, but the disadvantage when compared to Fisher test is that it is less robust. Fisher test is an exact test, while chi-square is an approximation of the p-value. It requires 5 or more observations in each cell, and it works with the central limit theorem. The central limit theorem, as you know, is that as our number of observations increase, each time we calculate the mean of our number of observations, the means are going to reach or to have a normal distribution. So if we have 30 observations and we calculate the mean and it's 31 observations, the mean is going to be 3, 32 observations is going to be 4, and so on. At the end of the day, the sum of all of these means are going to have a normal distribution, okay? That is the central limit theorem. As you can guess, it works with larger, here it is, and epileptic discontrol is going to be on the top of the table, the dependent variable, okay? Both are binomial yes or no answers, and we're going to put the data obtained after looking at the patient's speakers, okay? So once we have the table, we can calculate the expected frequencies. How are we going to calculate expected frequencies? We have to observe for each cell the number of the frequency of the outcome, the total number of observations. In this case, we have the frequency of the outcome is 70, the total number of observation is 100. For each cell, we're going to do a sandwich rule using the total number of positive cases or negative cases depending on the cell we're talking about. For instance, if we're going to use the first cell, here it is, you're going to do this. 70, the total of the column for the total of the cell per 60 over the total number of patients, 100. Okay, so 70 per 60 over 100 is going to be our first cell. In the second case, here, in our second cell, we're going to look at the total of the column per the total of the row, again, 70 per 40 over 100. We're going to do this in each cell, and we're going to take something like this. And what the test is going to do is to see if our results, the observed frequencies, are similar or not in their distribution to the expected frequencies if there was no difference between the group. That's what expected difference is, okay? There is no difference between the groups, so the expected frequencies should be these ones, 42, 28, 18, 12. But I have these frequencies. These frequencies are actually different statistically speaking. This is what the test is doing. How to calculate this? We're going to calculate the chi-square statistic. This is very easy. It's not that how this is the formula, but what we are going to do is to sum up the result of each cell when we subtract the difference between the observed and the expected frequencies to the square over the expected frequencies. The example is like this: 50 over 42 square over 42. Sorry, 50 minus 42 to the square root over to the square, sorry, over 42. And this is the result. We are going to do the same for each cell. And the results, we're going to do a simple sum, in this case using only two decimal places. And this is the final answer. With our chi-square statistic, remember that now that is 12.69. We're going to compare these results to our probability table using chi-square. To compare and contrast this, we have to know what our degrees of freedom are. The degrees of freedom are calculated using the number of rows, in this case 2 minus 1, okay, which is 1. And we multiply it between per the number of columns, minus 1, that is also 1. So our degrees of freedom is 1. This is important because, as you can see on the right, on the left side, sorry, the distribution of the chi-squares are different with each degrees of freedom. The more degrees of freedom, the distribution approaches normality, appears to approach normality. Therefore, the area of interest is going to be like smaller. In case of a normal distribution like this, no, the 0.5 area is going to be very small. We have, with less degrees of freedom, we have bigger areas. At the end of the day, we want to see our critic value, and if it stands in the 0.05 area, that is going to reject the null hypothesis, okay? In this case, we're going to compare the value in the probability table. We have 1 degrees of freedom, right? We want to use, in this case, I want to use 0.001 as my p-value, and the key statistic is 10.82. Ours is bigger, therefore ours is on the right side of the of the distribution, and we're going to reject the null hypothesis, okay? So we manually perform this test, rejecting the null hypothesis and saying the variables are not independent. There is a relationship between the variables. Be aware, as a common mistake, the K2 statistic test does not determine effect size, just whether or not there is a dependency between the variables, okay? Other measures such as odds ratio, risk ratio that can be calculated also with a contingency table better represent the effect size and the direction. But chi-square only tells us that they are not independent, okay? One is affecting the other. As first, at the end of the day, then what is a chi-square statistical test? To determine the difference between observed and expected data, it measures the difference between two data sets based on the chi-square distribution. When and why to use it? We are going to use it with independent categorical variables, okay? That can be more than two groups in each variable, but they are commonly used with binomial variables. How to perform it? You have to see step by step how to do it. We're going to calculate the expected frequencies and then calculate the chi-square statistic, and then contrast it with our chi-square table to see if at the end of the day the variables are independent or not. So as a conclusion, chi-square is a widely used statistical tool used to determine if there is significant difference between observed and expected data. It is used on binomial or multinomial, but at the end of the day, descriptive categorical variables, and it's used in research to test hypotheses about this data. It's very easy to perform. And that's everything. I thank you very much for your attention. Goodbye.